Good morning, everyone. So this morning I will speak about recent and future changes in ocean ice sheet interactions. I will mostly speak about ice shelves today. But first I would like to reply to a few questions to which I couldn't reply yesterday. So about the amount of fresh water that is in the different compartments in the southern ocean. So sea ice goes from 1,500 gigatons in summer to 1,600 gigatons in winter on average. Icebergs, they represent 3,000 gigatons on average. Ice shelf, a lot more, 650,000. And as Anna showed yesterday, the total Antarctica sheet is a lot more than that. These are just volumes. A large part of it will never go into the ocean. You can use SSP 585 during 500 years. It will never melt all of this because a part of it is grounded above sea level at a very high latitude, and so there is even in much warmer climate it will not melt into the ocean. Then there was also questions about the duration of icebergs travel around Antarctica. So I couldn't do like a proper analysis of that yesterday evening, but I show here 3 examples of icebergs that stay for very long in the Southern Ocean. This first one is called as C16. It stayed for almost 15 years in the Southern Ocean, and it went all around from the Ross Sea to here. But it's not really the time that it takes to travel little by little. It's because it gets grounded at some places, and at some point it meets a bathymetric ridge, and it stays grounded for decades, basically. That's what happened also to this iceberg that's calved in 67 and went to here in 78. So it can take a lot of time. This one, for example, stayed from 69 to 75 just here in front of the Filchner ice shelf. So it can take a lot of time for these reasons. And here you have a more recent example. It's the A68 iceberg that calved from Larsen Sea, and it calved somewhere, I think, in February 2019, and arrived here in February 21, 2 years later. So even when it drifts, it's not as fast as I thought, actually. Okay, any question on this? Yes? I don't know. Can we guess? I don't know. So it moves as the currents, as we've seen yesterday. Are the currents faster in a warmer climate? The coastal currents and so on? I don't know. There is a lot of space for research on icebergs, so you can really try to look at things and how it will change. We really don't know much. Other questions? If not, we move to the topic of today. So to give a bit of motivation again for these freshwater fluxes from Antarctica, I'm here showing so it's a plot that was prepared by Christophe Kittel at IGE. He's now in Liège in Belgium. So this is the total freshwater on average, annual average, that is coming from different sources. So you have sea ice in red. So on average, sea ice is producing brine rejections close to Antarctica, so it's a negative contribution to the freshwater flux. And then, as Martin explained in his presentation, there is advection of sea ice, so the sea ice moves away, moves to the north, and then melts more further from Antarctica. So that's really the cycle of sea ice that gives this. And then you have precipitations. Precipitations are very important if you go to the mid-latitude. It's really unfortunately, I didn't have evaporation, so you should have in mind that there should be evaporation that is subtracted to that. But here it's only precipitation. Evaporation is very important at mid-latitude, and when you go closer to Antarctica, the air is drier, and so precipitation is less important in the total freshwater balance. Then you have the ice shelves that are in orange. So ice shelf meltwater is here. It's positive freshwater. You have also the iceberg calving, and the two, if you average everything, the two are basically almost the same amount. And then you have surface runoff. You don't see it because there is almost no runoff. Just a little bit here, that's probably the Antarctic Peninsula. Yes? It should be. Yeah, it should be if you neglect multi-annual sea ice, but if you average over several years, it should be zero. Yes. It looks like zero, no? It should be. If it's not, there is a bug. No, this is from. So this is from a reanalysis that is forcing an ocean model. This is from an ocean model. I'm not sure that it would be so easy to do it with observations. And this is from a model that has been tuned towards observations. And this is the melting of the icebergs is from the model, but the calving is from observations. So the amount is correct because it's constrained by observations. And this is from a regional climate model. Because we don't know how to estimate this from observations. Okay? So what you see is that when you go close to Antarctica, in the place where you produce dense water, so this part is very important because that's where you produce dense water, that's where you produce convection, that's what will affect the thermoline circulation and so on. So this is the important part, and here the only thing that is able to kind of balance this is not so much precipitation if you go close to Antarctica, it's a lot the freshwater fluxes from the Antarctic ice sheet. And now this will evolve in time, and I think maybe every 20 years there will be a print of the dashed line so that you see how it evolves. So there is internal variability, of course, but what you can see that the sea ice is getting less and less important. So it's slowing down at the end. I don't know why, but it will reach 2100. So first, what you can see that there is more precipitation. This is something that you expect in a warmer climate. The air is warmer. It can hold more water before saturation, so it can transport more water towards Antarctica. So on average, at this latitude, you have more precipitation in the future. The sea ice seasonal cycle is reducing quite a lot. You have much less. So originally we were here, and then in the future, so I forgot to say this is a SSP 585 scenario, so it's quite a strong future, quite a warm future. You have much less sea ice production, and the sea ice production is really close to Antarctica. So you see that you have a lot less meltwater, a lot less sea ice production, dense water production than originally. And because it's compensated by melting, you have an average of 0, should be. And so you have less meltwater at mid-latitude. Then in terms of, it's not obvious to see, but if you look at the details, you can see that you have also a significant increase in the meltwater from the ice shelf and from the runoff as well. You see that runoff is no longer negligible. You can see that it appears everywhere. So you start to have melting at the surface of Antarctica in these kind of scenarios. If you go beyond 2100, it becomes very important, actually, it's a green one. But what you see that you increase this part, you reduce this part, and so if you look at the average, you at some point you no more produce dense water due to fresh water. So that's what's happening in the projections usually, and it can happen in 2100 or 2150, depends on the scenarios and on the models. But at some point, it always happens in the simulations. And this shows the importance of both sea ice, of course, and also the freshwater. And there are feedbacks also between sea ice and the melting of Antarctica. So that was for the motivation of today, to really take some interest for the Antarctic ice shelves. And now I'm going to speak about the Amundsen Sea, because that's the places actually where we've observed the largest changes, so I think it's important. It's not only because I work there, I think there are good reasons to be interested by this region. And we'll discuss whether the observed changes can be attributed to anthropogenic forcing. So I like to start always with a bit of history. So the Amundsen Sea is quite remote. It's not the first place where people went to Antarctica, and it's actually only after the Second World War that people went there with the ships that actually were created for the World War. There was no use of them after the World War, so they sent them to Antarctica with the planes that were on the ship that were going together. And this plane could go and take pictures of the region and map the entire Amundsen Sea. So the coastline was mapped in the 40s, and in the 60s we had clear view of the glaciers that were flowing in this region. So that's quite recent if you think about it. So that's the map of Antarctica. The ice shelves are in black with white contours. If you look at it, you immediately see that there is the Ross and the Ronny ice shelf. And a lot of people were only interested by these two ice shelves at the beginning, and I think it makes sense. We probably would have done the same if we had this map of Antarctica. So the interest before the 80s was mostly on the Ross and Ronny Filchner ice shelf, in terms of glaciology and in terms of oceanography. So in the early 80s, thanks to the methods that I presented yesterday, people started to have a clear view of the thickness of the ice, thanks to the seismic echo sounding and then to the radar. And they understood also that Pine Island and Thwaites glaciers drain most of the ice that is below sea level in West Antarctica. And Thwaites and Pine Island are these two little ice shelves. This is Thwaites, this is Pine Island. But they have large drainage basins. That is in pink here. And these drainage basins, so drainage basin is all the ice that will eventually flow towards the ice shelf. And these drainage basins are largely below sea level. And so that they understood at the time, in the early 80s, that if there was a danger of strong contribution to sea level rise, it would probably come from these two glaciers, Pine Island and Thwaites. And in 82, there was the first mass balance estimation of Pine Island Glacier. So they used radar from planes and Landsat satellite data, which was launched in 72 by the US. And so this is a picture of Landsat. So Landsat was used to know the velocity of the glacier. They found some features at the surface that were moving, and so they were able to track them and to kind of guess the velocity of the entire glaciers. They found these two people, Richard Captree and Christopher Dawkey. They found that the glacier was gaining mass, but they wrote that errors were so large that such conclusion should be regarded as a tentative. So, but they still thought that the glacier was gaining mass. Then came new technology, radar from space, ERS satellites. And then Barbel Luchita found that there was a mass loss. She calculated that there was a mass loss. This person, she's probably the first woman in this story, and she came from the moon. She came from she did the pictures that helped the Apollo mission to land on the moon. And when all the moon program was over in the US, she moved to Antarctic science, and she focused on Mars also, but she also moved to Antarctic science. And then she did this kind of map. The radar data are much better than the Landsat because you can see through the clouds, and there was also a higher resolution, and she could identify very clearly crevasses along the glaciers, and from that you get much more accurate velocity of the glaciers. So she found a mass loss, but she concluded that it was less positive than expected. But if you look at the numbers, she found a mass loss. And but she also concluded again that errors were so large that overall it remains poorly known. Just before this paper of Luchita, there was a campaign, actually an oceanographic campaign in the Amundsen Sea in 1994 that was led by Stan Jacobs from the US, and on which there was also Hartmut Helmer. And they started their travel from the Ross Sea, and as always, as everywhere else around Antarctica, they started by measuring cold water, water at minus 1.9 degrees, the surface freezing point. And they thought that it was more or less like this all around Antarctica. But when they arrived in the Amundsen Sea, waters got much warmer, and they had this kind of profile. So this is like the freezing point, and this is what they measured. So at the surface, it was at the freezing point, but going at depth, it was reaching 1 degree. So 3 to 4 degrees above the freezing point, meaning that there was weakly modified circumpolar deep water that was reaching the vicinity of ice shelves. So that was the first time it was observed. From that, they calculated that basal melt rate beneath ice shelves were 1 order of magnitude greater than anywhere else around Antarctica. And they also, thanks to the help of Adrian Jenkins, they also calculated the mass budget, and they found that the glacier was losing mass. But again, there were huge uncertainties, and it was not a very clear conclusion. The paper that they published was published 1 year after Lucita. Okay, so the big change came with that. So that's some work that was done by Eric Rignot in the US, and he used another method. So he used again the ERS radar data, but using interferometry. And so maybe you've seen this kind of maps sometimes in presentation. This is an interferogram. And it basically shows the interferences between several radar pictures taken at different moments, different times. And because of tides, the floating ice shelf is moving like this. So if you take 2 pictures, you will see you will see differences in phase, and you can make interferences between the 2 pictures, and you have these kind of things. In the grounding zone, in the part that is just near the grounding line, you have these kind of stripes, and from that you can guess that the grounding line is here. So that's what it did. That was quite new. That's quite complicated if you want to do it properly. And that's what he got on these pictures. And he found that the grounding line of Pine Island was retreated by 1.2 kilometers with a relatively small uncertainty from 92 to 96. And if you assume that the ice shelf is floating, you can guess the ice shelf thickness, and then it meant that the ice shelf had thinned by 3.5 meters with a reasonable uncertainty. And a few years later, he did the same for Thwaites, and he had very similar numbers. So that was quite a revolution. There were a lot of discussions in the following decades to know whether this was correct or not, whether this was variability or the sign of climate change or these kind of things. But eventually, it made its way, and rapidly. So at the beginning, they thought that maybe it could be due to changes in surface accumulation, but quickly they found that there was no change of surface accumulation, that there was actually an observation, an acceleration of the glaciers that you can get from the satellite imagery, and also higher basal melt rates than anywhere else around Antarctica. So this led to this view that we got on the situation, that the mass loss of West Antarctica was due to changes in ice dynamics that was triggered by increased melting by the ocean. And that more and more studies came and confirmed this view. Any question on this first part? If not, let's keep going. So now the question is, okay, we had a change. The Amundsen Sea is warm, but has it always been warm or not? When did it change? And how? What are the mechanisms that led to this change? These are paleo data, so everything is reversed. So the time axis is reversed. So this is the present and this is the past. It's warm where it's blue. So blue means presence of circumpolar deep water, and the axis also it's warmer when it's here, and it's cold when it's here. So they usually do that in paleoclimate. They reverse everything. But so this study is based on studies of of isotopes in foraminifers, in the sediments. And what these studies shows is that there has been a transition approximately 7,500 years ago and before. So from that period, 7,500 years ago, to recently, there was cold water in the Amundsen Sea, and only long time ago there was probably circumpolar deep water that came in the Amundsen Sea and that removed all the ice shelf at the time, because the ice shelf were extending much further. You have the same picture for different locations, and if you do that for the for the recent period, you have also cold water here and a change that appears somewhere between the 40s and the 60s. So that's what you can get also from the foraminifers. So there seems to have been a transition recently that was unprecedented over the last 7,000 years. You get also a picture when you look at the sediments. So I'm not able to give you the details of exactly why they looked into the sediments, but they looked at the sediments under the ice shelf in places where it was grounded before, and so they could figure out the date of ungrounded. And so what they think is that there is a ridge here. So it's a study by Smith for Pine Island, and they did a very similar one from Clark about Thwaites Glacier. So the ice shelf was grounded on a ridge before the 40s, and during the 40s, and between the 40s and the 70s, there was a retreat of the ocean. The fact that it started to open changed the situation in terms of sediments, and then at some point there was a complete retreat of the ice shelf, and it got ungrounded to the position that we have now. Okay, so there are multiple lines of evidence suggesting that there has been a change around the 40s from cold Amundsen Sea to warm Amundsen Sea, and a retreat of the ice shelves. Now we'll speak a bit about the ocean dynamics, because if we want to go further and to try to understand what happened and if it's related to anthropogenic forcing, we need to dig a little bit into the mechanisms. So we need to understand what favors the intrusion of circumpolar deep water in the Amundsen Sea. So here you have the continental shelf. The ice shelves are somewhere here, and this is the deep ocean there. If you have an eastward undercurrent, an eastward current that is flowing that direction along the continental shelf break, you will have, for this to happen, you need a pressure gradient like this. You will have a bottom drag like this and Coriolis like this, and the balance makes the eastward undercurrent going a little bit upslope, and this is favorable for the intrusion of circumpolar deep water. Another situation that is favorable is that as the eastward undercurrent is meeting a bathymetric trough, it undergoes vortex stretching, and this will create this kind of circulation that also favors the intrusion of circumpolar deep water towards the ice shelf. And these situations are not possible with a westward undercurrent. So you just need to keep in mind here that the eastward undercurrent favors the intrusion of circumpolar deep water from the deep ocean to the continental shelf. And now this is cross-section of the Amundsen Sea. I'll describe it a bit if you don't need to remember all the details, but I will summarize after. If you like this kind of plot, you can also try to draw it yourself. You put some winds, you try to see how it works. So this is a fresh shelf. So this is how it probably was in a cold climate before the 40s. So what you get in this case, you have the easterlies that are here, the westerlies that are here. The easterlies will push water at the surface towards Antarctica. This will increase the surface slope. And at the same time, because it's a cold climate, you form a lot of sea ice. So you mix everything here and it's cold. So you have this kind of situation. So you have something that is without any stratification at this stage. And so you have an Antarctic slope current that is in balance between the pressure gradient due to the surface and Coriolis. And in this situation, it's not favorable for the intrusion of circumpolar deep water, so it will be quite stable like this. If then you start to shift the wind system towards Antarctica, you move the easterlies a bit that direction, the westerlies a bit in towards Antarctica, you will start to move the place where you have this upwelling towards the continental shelf break. And at the same time, because it's a warmer climate, you form less sea ice. So you have less deep convection, less mixing, and then you end up with this situation. If you have this situation with this stratification, the density gradient of the stratification will go against the pressure gradient of the surface, and this can reverse the eastward the current. And so you can have two currents that flow in opposite directions from the surface to the bottom. This is the eastward undercurrent. It has actually been observed in the Amundsen Sea. And the Amundsen Sea is a complex region. There is also the Amundsen Sea law. It's not only westerlies and easterlies. And so sometimes you can have also a reverse situation with the slope that is increasing offshore. So in this kind of situation, this can create an eastward undercurrent that will start from the surface and that can go all through the column, sometimes decreasing at depth depending on the local density gradients. If you go to a warmer climate, there is no more sea ice. So this is like a much warmer climate. This is like 2300 in a warm scenario. In this case, you have no more sea ice formation, but a lot of fresh water that is coming from the Antarctic ice shelf. So you have only warm water everywhere, but density gradients like this that are coming from the ice sheet. And then in this case, you tend to have less penetration of circumpolar deep water, but it can still be favored because the Antarctic slope current decreases due to this density gradient related to ice shelf melting. So this is like the average situation. So what you need to remember from that is that winds are very important for what's happening in the Amundsen Sea, especially the transition between westerlies and westerlies. Freshwater fluxes are important, especially those related to sea ice and the ice sheet freshwaters, because they will change the density gradients. And then you can also have an importance of offshore advection because they will change the densities offshore, so they will change the gradient. And in particular, the Ross Gyre, it's expected to extend in a warmer climate, and this is expected to also affect what's happening in the Amundsen Sea. So now you've seen that the winds are important. So what controls the winds? And in this paper by Ding in 2011, I think that they might be the first to show these Ross B wave trains connecting the central equatorial Pacific to the Amundsen Sea. So this is pressure anomalies in the atmosphere that are created when you have this kind of sea surface temperature anomaly in the Pacific. And if you want to, so the way I see why atmospheric pressure gradients are propagating like this is that you have a lower Coriolis parameter in this part than in this part. So if you want to keep the geostrophic balance, it means that you will need a stronger velocity here than here. And because of the friction, you also have velocities that goes into the interior. So if you do the average of these two velocities, it moves the lows in that direction. So okay, that's what's happening. The Amundsen Sea is here, so you can guess from this that the Amundsen Sea will be very affected by whatever happens in the equatorial Pacific. So now I need also to speak about something else before going further into the importance of winds. I will say a few words, probably many of you know that already, but to be sure that we speak about the same things, I will speak what I have in mind with climate variability. So climate variability, you can split it in internal variability. That's variability that emerges from, so you have constant daily and seasonal solar forcing, no internal variability, no multi-decadal variability or whatsoever. But your system, your climate system is creating some variability. And for this kind of variability, there is an importance of non-linearities like eddies and these kind of things, and also feedbacks will generate all these kind of variability. So if you have a constant forcing, you still have your model that varies in many directions. It can be quite important. This is an output of the IPSL climate model. This is the global surface air temperature anomaly from a simulation, a control simulation in which there is no change in the forcing. And you still see that there is a slow, multi-decadal, even centennial variability that emerges in the system. So if you do even like a 100 trend, in one of these simulations, you will get a trend that can be quite strong, that is actually due to internal variability. So whenever you try to do trend and attribute to anthropogenic forcing, you need to be very careful with that. Then you have the other part. The other part is forced or external variability, and it can be split into natural and anthropogenic variability. Natural variability is everything related to volcanoes, solar cycle, or even orbital parameters. And anthropogenic forcing, it's us. So it's the greenhouse gases, ozone, aerosols, and changes in land use. So let's see what people have done so far in terms of attributing what's been observed in the Amundsen Sea to the anthropogenic forcing. And so there is a lot of space for research in this area. There are not many papers, and that's a very hot topic. So there is a lot of space for very nice contributions to try to attribute what's happening in Antarctica to anthropogenic forcing. And one of the few papers that have looked at this has actually looked at the winds that you can see with the pressure systems here. So this is don't look at the colors, just look at the pressure contours, and the pressure contours give the wind. And so this is the total trend in pressure from 1920 to 2000. And you see that there is a clear signal that is here in the region of the Amundsen Sea. And this is only the internal variability, and this is the external variability, and this is the greenhouse gases part within the external variability. What you can see is that it seems that basically the signal that is here is the sum of this internal variability and the greenhouse gases signal. What it shows, what is important here, is that it's very similar orders of magnitude. So what's happening in the Amundsen Sea, there is a part that is significant that comes from greenhouse gases, but there is also a very strong internal variability, and that makes it very complicated to identify what's happening. And in this plot, you see the signal of the IPO, the interdecadal Pacific oscillation, that you can view as a interdecadal El Niño signal to simplify it. And you see that it's kind of related, suggesting that this is indeed the signature of the natural variability in the tropical Pacific. Okay, so the view that we have about what's happening in the Amundsen Sea. Yeah, I didn't find the right time series, so it's a fake time series. I plotted it myself. But this is so don't try to find the spot that you know perfectly. But the way we see it is that there was a strong anomaly in ice shelf basal melting sometimes in around 1945. And then, if there had been no anthropogenic climate change, there would be then, at some point, a colder phase. And then, if you let it long enough, the ice shelf could re-advance. But due to anthropogenic climate forcing, there was just a small anomaly on top of it, so that what happened in 1945 might have been due to natural variability, but it's the recovery that was prevented by the emission of greenhouse gases. And I didn't speak about it, but there are other pieces of evidence showing that this event can emerge from natural variability. It's strong, but it can be found just due to natural variability. Okay, and on top of this, there might have been also an ice sheet tipping point that also prevented the ice sheet to regrow back to the state that it had before 1945. And so this is the marine. This is the marine ice sheet instability. Let's do a bit of glaciology. So this instability is very important. It has been suggested from the 60s, but it's only in the year 2000s that Christian Schuf brought like mathematical evidence that this can really happen. So I'm going to try to explain this. I took a lot of time to understand it, and I'm not sure that I understood it completely. So let's see. So we have two situations here. The only situation is that the bedrock is different in the two cases. Here you have a bedrock that is deepening when you go towards the deep ocean, and you have the opposite here. You have a bedrock that is deepening when you go to the interior of the Antarctic ice sheet. And so let's assume that there is a grounding line retreat in the two cases. So it's going from the solid line to the dashed line in the two cases due to increased ocean melt, for example, but it could also be due to changes in the surface mass balance or whatever. And let's see if the retreat of the grounding line can be stable in the two cases. So what's important to have in mind in this theory is that the thickness at the grounding line is at the limit of the flotation. So if you know the depth, you know the thickness of the ice sheet above the grounding line because it's just at the limit where it's floating. So from that, you know that if you go from this situation here to this situation here, you will decrease the thickness of the ice shelf. And it's the opposite here. In this case, you just increase. You have to increase the thickness of your ice shelf if you go from this situation to this situation. That's the first point. And then the ice sheet is always a balance between accumulation and ablation, or accumulation and export through the grounding line. So if you reduce a little bit, so you have a balance between what's falling, the snow that is falling on the grounded part, and what's going through the grounding line. So if you retreat the grounding line, you will have a little bit less accumulation in total for the ice sheet. That's the so A times delta X will be the change in accumulation. So it means that you need to decrease the flux at the grounding line because it has to be like this if you want a steady state. And then also, when you retreat the grounding line, you reduce a little bit the friction here at the base. So you also have to reduce the velocities at the grounding line. So basically, you have to have a balance between the changes in the flux at the grounding line, which is a term due to the change in thickness and a term due to the changes in velocity. And in this case here, and then you have a reduced accumulation. So in this case here, this is negative, and this is positive and negative. So it shows that in many situations, this can be verified. You can find a position where this will work. So in this kind of situation, usually it's possible to find steady states. In this situation, it's the opposite, because here you have something that should be negative due to the surface mass balance, but here these two terms are positive. So it shows that a balance like this cannot exist. So basically what's happening is that if the grounding line here starts to retreat, the flux at the grounding line will increase. It has to be like this. Whereas in this case, it will change very little and sometimes come back to balance. So this situation is considered as completely unstable, and this instability is called the marine ice sheet instability. And of course, this is a simple theory. It's like a flow line. In reality, you can have pinning points, so you can have like little mountains that come in the middle of the ice shelf, and that will change a bit the story. And you also have lateral friction. So lateral friction is important because it has been shown that even in this configuration, if you have certain types of lateral friction, you can also have steady states. So this is just a simple picture to explain that in general, when you have a bed like this, a bed that is increasing towards the middle of Antarctica, it will be more favorable for marine ice sheet instabilities. But then you need a more complex ice sheet model if you want to really resolve something realistic. Okay, back to ocean science. So there is an instability. There is it can be considered as a tipping point from the ice sheet dynamics. Are there similar tipping points in the ocean? And there has been papers by Hartmut Helmer some years ago about what's happening under Filchner-Roney here in the Weddell Sea. And So basically what they did is that they started to do climate change scenarios. So at some point, warm water went into the ice shelf cavities there. But once the warm water was there, it was triggering a self-induced circulation due to ice shelf melting that actually helped even more warm water to go into the cavity. And then, even if they reverted to a cold climate, the warm water was still going on in the cavity, and it was never stopping. They had to, in their models, they had to shut down the melt to be able to get cold water back to the system. So that suggested that there was also an ocean tipping point, and there is also this paper by Hazel from 2 years ago. It's similar results for the same ice shelf, but they explain it in a different way. So what they did is imposing wind perturbations in this area, and then starting from a cold state in the cavity, they change the wind, and at some point it's getting warmer. And then when they revert the forcing, it stays warmer for much longer than on the first way. So this is a hysteresis. And the way they explained it, it was an interplay between these two water masses in front of the cavity and the feedback of the ice shelf. So if you have warm water that is going into the cavity, it will create more melt. No, if you have, let's start like this. If you have high salinity shelf water, so cold dense water going into the cavity, it will create some melt, but the melt will then feed back into this layer of salty water. The salinity will decrease until the cavity, this water mass is not dense enough, and the cavity is filled with warm water. So you can have these circulations like this. So in theory, you can have also tipping points in the ocean, but I have to say that with several models, we did a few simulations about this with more realistic forcing, more realistic environment, not only in these cavities, but in other cavities as well. And we did not find such ocean bistability, so that's still a matter of research as to whether this can happen or not in a real ocean. So summary of the first part. Melting beneath the ice shelves in the Amundsen Sea is driven by winds and buoyancy fluxes. You need really the two ingredients. For a long time we thought that it was only the winds that were driven this, but recent papers show that buoyancy fluxes are important as well. A large part of the wind trends is related to internal variability, and a small part is attributed to greenhouse gases. We don't know anything about what's happening with the buoyancy fluxes. And then the ice sheet in the Amundsen Sea sector may have become out of balance or crossed a tipping point in response to relatively small anthropogenic forcing. That's the picture we have now, but it's based on very recent results, and this picture may evolve in time, or some people might disagree with that. So now let's speak about the future. So we've seen the past. So this is the part that has changed the most in Antarctica, the Amundsen Sea, and now we need to move to the future. I'm going to try to be a bit fast on this. The first projection, we start with a bit of history again. The first projection of the fate of ice shelves was actually done a long time ago by John Mercer in 78. Mercer had geomorphological indications on previous West Antarctic collapse during the last interglacial period. So that was a motivation for him to go further. Just before his paper in 78, Bert Bolin went in front of the US Congress and explained that the CO2 concentration could double in the next 50 years, which would have been 2028. And at the same time, there was also the first results from from climate simulations that were created at Princeton. And these first simulations that were published in 75 showed that global warming could reach 1 to 3 degrees globally for double CO2 concentration. So in 50 years, according to him. And then they had, so it was a model only of the northern hemisphere. There was not the southern hemisphere, but the polar amplification was quite strong. And for this kind of global warming, they had plus 10 degrees at 80 degree north, and they assumed that it would be the same in the south, so that you could have 10 degrees of warming in the next 50 years then. Then there were also theories emerging at the same time, suggesting that ice shelf in West Antarctica could lead to a collapse of the entire ice sheet. And that was the first version of the theory that I explained just before, of the Maisie theory. And then there were also extensive observations by Robin and Addy suggesting that present-day ice shelves do not exist where the midsummer air temperature exceeds 0 degree. That's just observation. And so from that, and from the present-day temperature of the ice shelves, he concluded that Ross and Filchner-Roney ice shelf, that were approximately -5 degrees, could collapse in 50 years due to this warming. So that was the first projection. Of course, there are many things that we know better now. It's good because it didn't work for nothing. So the doubling of CO2 based on their concentration is more like 2078. The polar amplification is not as strong in the south as in the north, or it's not that it's not as strong, it's that it comes much later. In 2100, in most simulations, you have similar warming as the global warming around Antarctica. And also, he focused a lot on Ross and Filchner-Roney ice shelf because that were the two big ones, but we know now that Pine Island and Thwaites are the ones that are important. And then also what he said in this paper is that a warning sign would be the collapse of ice shelves in the west, in Antarctic Peninsula, and that actually happened a few years later. The Prince Gustav Channel and Larsen A collapsed in '95, this ice shelf. The colors here are the dates from the 60s, the decades from the 60s to 2010s. And then Larsen B collapsed completely in 2002. You have strong retreat of the front of Larsen C. Wardy ice shelf here collapsed also in 2009. And you have also retreats on other parts. And this is a more detailed view of Larsen B, showing the retreat, 98, 99, 2000, and 2002 completely. So this is often attributed to hydrofracturing, so processes happening at the surface. You have warmer air, you have meltwater that is created at the surface. The snow is full of water, so it cannot go into the firn, has to stay there or to flow into the ocean. And you can see it from the satellite pictures. And then, so this is like the main theory of disintegration for Larsen C or Larsen B, is that the meltwater is filling the crevasses, and because water is denser than the ice, it creates a pressure that tends to open the fracture more and more, and then it helps to disintegrate the ice shelf. So that's the main thing that people say about Larsen B. But it's very important also to understand that there is a preconditioning of the ocean. The ocean is really the important piece in there. It has been shown already a long time ago by Andy Shefford. He calculated the thinning of the ice shelves. You have a lot of uncertainty, but you can see it from the satellite pictures of the time. And this thinning has to be induced by the ocean. It cannot be due by the surface processes. And so that's basically the picture you need to have in mind. That if you want to collapse an ice shelf, you first need to thin it. Otherwise, it will never be. It won't happen anything if there are ponds at the surface. It has to be thin enough. And then when it's thin, then you can have surface processes that create crevasses everywhere, or mechanical processes, and then you can collapse your ice shelf. That's more or less how it happens. I will go with that. So this is something that I took from a paper by Shefford and Nowicki in 2017, and I updated it by putting the results for AR6, but that's their plot. So this shows the contribution to sea level from the Antarctic and Greenland ice sheet in the IPCC report, from the first report, second report, third report, and then on. So for the three first reports, the picture that we had was like Antarctica is gaining mass, because at the time people thought that the ice dynamics was too slow. That was only important for the paleo timescales, the very long timescales, but was too slow to evolve on decadal timescales. So the only signal would be increased accumulation in a warmer climate, because the air can hold more humidity. And for Greenland, it's the opposite, because it's already warm, so warmer air means melting at the surface. So that was the first picture of the three first reports. And then, of course, in 2001, already we had the results from Reno showing that there was actually mass loss in some places of Antarctica. And in the next report, in 27, they came with some kind of additional contribution that was due to the ice dynamics, and it would mean that there would be additional mass loss from Greenland and mass loss that is compensating the surface mass gain for Antarctica. Okay, that was based on empirical state. That was an empirical statement. That was not based on much. In AR5, what they had is a few more ice sheet simulations because the ice sheet models were not able to reproduce the signals before, and then they were more and more able to do that. And then the contribution of Antarctica, the dynamical contribution, was also much stronger in the last report. And that's the first time, I think, in the last report that there were ice sheet simulations directly connected to the results of the CEMIP models. And that's what showed the satellite data, so that they show that basically the first estimations were wrong. So, I mean, it's not to blame anybody. I think that we just didn't have observations to do the right projections at the time, but it's to show that we are still in a world that we don't know much. It's not something that, so it means that we have moderate confidence in these results, and it means that we have also a lot as a community to bring to these kind of simulations. What is incorrect?
So the observations here show melt rates that are on par with the projections. So if you go to the end there, the most recent observations are actually already where the projections on the left-hand panel are, if I read that correctly.
For Greenland?
Well, I guess.
As a whole, like this one and this one? Yeah, so I don't know actually, but so Antarctica, so first now we are not there anymore, we are here, so that's not state of the art. But Antarctica is weird, like if you go to the warm scenarios, even now, you still have quite a strong contribution of surface mass balance. Surface mass balance, there is no trend that has been observed, but we think that at some point it will start. But in the models, the trends in surface mass balance start in the 2000s, and they, in many simulations, they compensate exactly the dynamical part. So in ISMIP 6, many models had a positive contribution, so negative contribution to sea level. So yeah, but I don't know the details. But yeah. And you don't know also this one. You don't know what is the part of anthropogenic forcing or what is the part of variability as well. So some people say the models are wrong because of that, because you compare this, and you say it's not possible, the models are wrong. But then how do you know? There is also internal variability. Okay, so before concluding, I'm going to speak about Rube Goldberg. So Rube Goldberg is the guy who is drawing these kind of cartoons. He likes to do very complicated machine for very little. So this is a machine reminding the guy to mail a letter when he goes here. And this is a machine to squeeze oranges. And this is a machine to have, I don't know how to call it, but so that you have a clean mouth after eating. There is actually a contest. It's a Rube Goldberg machine contest that is happening every year. And I think that when you develop climate models or any model, I think that you need to think as to whether we are playing this kind of a Rube Goldberg machine contest. So the question here is, should we work on the inclusion of ice sheets in the climate models? Climate models are already very complex. There are good reasons for why we had to put the oceans. There are good reasons for why we had to put sea ice and biogeochemistry and so on. Do we need to put ice sheet, or is it just making the models more complex and less reliable? So before concluding, I will say a few things. So this I showed yesterday. I think it's a major motivation that a lot of the freshwater in the Southern Ocean is coming from the interaction with the ice sheet. If you don't have interactive ice sheet in the model, you are not able to have mass change, or you need to prescribe it, but you will never have this as a result of climate change. This can affect things that are important for the climate, Antarctic bottom water, sea ice concentrations, and feeds back also to the melting of ice shelves. And first, there are also some other more local motivations. The two pictures is one simulation of the Amundsen Sea. So it's the change, the response to a kind of forcing. And you have a slight warming, but not much. It's because here you don't have any melting under the ice shelf cavities. And once you switch on melting under the ice shelf cavities, it will create a much stronger warming. So this will feed back to the ice shelves. And this is very important. There are also other feedbacks. When you start to retreat the grounding line, you will expose more ice to deep water, so more ice to cold water. And here is two situations. This is the ice depth of the ice shelves. In one situation in the present day and one simulation in the future. And this is just the melting, the change in melting profile that is coming from this change in geometry without any other changes. So here you can see that the melt rates are increased by 50% just by changing the geometry. So it's very important also to have this kind of feedback. And this is another kind of feedback where you have a ridge. And if the ridge is too close to the ice, there won't be any possibility for the warm water to go there. But if you start to increase the gap between the two, then you will allow the warm water to flood the cavity, and then you will have your feedback on the fresh water. So I will stop here. I think it's time, JB, no? Okay, so I finish with this picture then. So this is actually an ice sheet ocean coupled simulations. What shows this picture is the bottom temperature of the ocean for the present day, and then we will impose a very strong perturbation. We will immediately switch the ocean to the state in 2300 on the SSP 585, just to show what's happening in a simulation where we can see things. And this to illustrate how it goes when you couple an ice sheet to an ocean model. And so you have basically at present day, you have warm water in the Amundsen Sea, but most of the places you have cold water all around Antarctica, blue. And then when we change, there will be increase. Okay, it's moving. So let's focus on this place, for example. So you have the present day simulation, and then now we do the perturbation. So warm water at some point is entering the Ross ice shelf cavities. It's flooding all the cavities. And then when it's reaching the grounding line, you can see that the model is able to expand the ocean under the ice. So that's a result of melting and ice dynamics. And so the ocean is expanding and the grounding line is retreating. Then at some point, we switch it back to cold water. And what you see here is that the grounding line is not going back to its previous state, at least not until, if you wait 500 years, it will go back, but it's very slow to go back to the previous state. Just to show that coupling is important, to have the grounding line retreat and so on, and to also have the dynamics because it will create instabilities. This I skip. I think before don't skip. Before concluding, I think it's important to have in mind the structural uncertainty that remains in the system. It's a thing that people can work on. First, you need high resolution if you want to show the melt rate. So to make it short, these maps shows in red the places where melting is important for the ice dynamics, and in white it doesn't change the ice dynamics. So it shows that melting is important only in these tiny little channels at the bottom of the ice shelf cavities, and it's important to have this in mind because at the climate resolution, the resolution of climate models, ice shelves look like this, and we don't resolve these tiny little parts. So this needs to be resolved or parameterized. Something that we don't know much as well. This is a picture of the Nansen ice shelf for a melting event that didn't last very long, but that was quite impressive. We don't model these kind of things in the future. So if runoff becomes important, we are not able to transport the meltwater at the surface of the ice shelf. And there is a lot also that we don't know on ice damage, calving, that is also extremely important for the models. And so there is a lot of things to work on anything that is related to ice shelves, actually. I will stop there.